Okay, folks, in this lesson we're going to look at some tutorial problem solving related to conservation of energy. Hopefully you understand conservation of energy from previous lessons. We're just going to look at a very simple scenario just to remind you of what's going on here. We have a giant who's got a sort of death wish for some clowns, and he would like to do the clowns a lot of harm. He sets up this pendulum, playing a trick. Clown A is watching and wondering what's going on. Clown A's evil twin, I guess, Clown B, is standing none the wiser, facing away. The giant lets this pendulum go. The question would be, does this ball, if the clowns are standing the same distance away from this pivot point, will the ball hit Clown B? Now, if you understand conservation of energy, you would know that you cannot get more energy out than you put into a system. You cannot create energy out of nothing. And so we would expect that this ball is indeed not going to hit Clown B. That it would simply, the best case scenario where there's no friction involved, it would come right to the same area and it would touch Clown B's hair just like it was in Clown A. It's very important to note that in the real world there would be various factors that of course would be slowing down this object. And if we look at on screen, we can see that right around this point here, there would be rubbing and friction. There's also a little bit of air friction. And so what we tend to get is we would get this motion of a swing, and eventually it would go and eventually it would stop. And the reason why it stops is because there's energy leaving that system. So these are real world it is a real world example of a conservation of energy situation. Energy is conserved and changed from one form to another. In reality, there's energy leaving that system in the form of friction and heat. So we're just going to look at a couple of examples, worked examples of that. So the first example that we're going to look at, there is a watermelon sitting on a table 1.2 meters above the ground. What is the potential energy and kinetic energy at the top, and with what speed will it hit the ground? So we're going to have to solve this using conservation of energy. Do you have to solve it using conservation of energy? No, you can use your kinematics equations to solve this, but sometimes you may be asked to use conservation of energy concepts, or it may be actually the quicker way to solve these questions. So what is the potential energy and kinetic energy at the top? Well, this is a nice easy one for us to set us up, I think. So if we look at the potential energy at the top, PE, we know that potential energy is equal to mg delta H, and that delta H means this H point from this H equals 0 reference point. And normally that's the ground, not always. But in your conservation of energy examples, you would set a point in your diagram in your system as H equals 0. It makes sense to set the ground as H equals 0 in this case, in a lot of cases. And the watermelon is 1.2 meters above that. So we would need to know the mass of the watermelon. And if we just have a quick look here, it's a 3 kilogram watermelon. Okay, so we can put that in. We have a 3 kilogram watermelon. We've got G, which is approximately 10 meters per second squared, 9.81 we know, but that's approximated for this. And you have 1.2 meters. And you're just going to multiply those together, and you're going to get 3 times 10 is 30, and then 30 times 1.2 is 36 joules. So this is our potential energy. Kinetic energy at the top, it is not moving. V is equal to 0, so the kinetic energy is 0. A half mv squared would be 0. So your Ke is going to be equal to 0 joules. So in essence, the total mechanical energy that this system has at the beginning is 36 joules. Now in conservation of energy, basically states if we treat this as a closed system, rather, the total mechanical energy does not change throughout this throughout any events that happen in time in this system. So with what speed will it hit the ground? So we know that the total mechanical energy is going to be remain the same. So whatever energy this system had in total at the beginning, it will have at the end. So what happens to the energy involved here? Well, if we look at our energy, we have to look at our energies at the beginning and at the end. Now, the first thing that we should do is we should set up a scenario. We should set our event points. So this might be event 1, where the watermelon is up where it began, and event 2 is just before it hits the ground. Okay, because when it hits the ground, there's a force acted upon it, and that system is changed and altered. So at the very beginning, at time 1, we know that it is all potential energy. So we know that the majority of this energy, all of the energy, is potential energy. And we know that there is no kinetic energy because we've established that. At point 2, just before it hits the ground, what we see is that it is now transferred to a scenario where it is all kinetic energy. And the reason for that is because there is no potential energy at point 2, because there is no delta H at this point here. In other words, it's at H equals 0. So it's transferred from all potential to all kinetic. So when we're asking what speed will it hit the ground, we've got to, of course, set up our conservation of energy equation. Mechanical energy 1 is equal to mechanical energy 2. We write out the different energies involved. Now, you may have also elastic spring potential energy. That would be another type of energy that could be involved. But in this case, we just have potential, gravitational potential, and kinetic. So at the very top, it was all potential. In other words, there was no kinetic energy. At the bottom, it is all kinetic. There is no potential. So in actual fact, we can rewrite this as mgh1 is equal to a half mv squared. And when we do a little bit of rejigging, but before we do that, I guess we can acknowledge that we actually don't even need the masses because they'll cancel. And if we simply now isolate for v, we're going to get v squared. This 2 is going to go above the line and multiply by gh1. So we'll get 2 times gh1. So v squared is equal to that. So v is equal to the square root of 2gh1, or sometimes you'll see that as delta h. And then we would just plug in these numbers, and we would see that it's equal to the square root of 2 times 10, which is 20, times 1.2, which is equal to 24. Okay, and this would be meters squared per second squared. And that's going to give us our v value here. So pretty straightforward. But know that you can calculate the velocity at any point. For example, we could get the velocity at this black line here. Now, if you do that, be very careful. You would have to write out again your ME1, ME2 statements, and you'd have to acknowledge that in this case, at this point, maybe halfway, there is both potential and kinetic. So you would have to make sure that you account for that. Okay, so we're going to look at an example that's a little bit more complicated, and one which will hopefully allow us to differentiate between this notion of a closed system and an open system. So the last one, we assumed the system was closed and that there was no friction, no external forces in or out of the system. And we're going to start with that and then move towards an open system. So if we have a scenario where we've got one lucky young child on a roller coaster having the time of their life, and they're moving from A to B. As we saw previously, we can easily figure out, if we know a couple of things, we can figure out what the velocity will be at the bottom. If we know that height value at the top, we can isolate for V2. But what if it's an open system? And what if the there is a screeching noise and heat being caused by friction between the tracks and the roller coaster cart, as is the case in the normal world. And so what we need to do is if we are looking at an open system question, we will see things like mu k, the coefficient of kinetic friction. We will see a mention of work or distance or something which would allow us to calculate work. So here we've got mu k, we've got delta d, which is the path taken by the cart, which the force is acting upon. And we also have the mass that would allow us maybe to get things like the force of friction. So if we look at an open system, we cannot, in this case, we cannot just simply say MEA is equal to MEB. We cannot do that because we have this scenario where there is work being done by the system. So in actual fact, this system, as it moves, as the cart moves down, it is losing some energy. So there's work being done by this system, and energy is being released into the atmosphere, removed from the system. So we have to actually account for that work value. And we have to recognize that there's going to be a difference between MEA is not going to be equal to MEB. And that difference is what we call work. And our work energy theorem would tell us that. So we do know that at the very beginning, the total mechanical energy was presented and was given to us by mgh1. And we know that at the end, or let's call it mgha, just to keep consistency. And at the end, it's a half mvb squared, so it's all kinetic energy. But we have this lump that we've got to recognize, because there is going to be energy removed from, taken out of this system. So we've got to make sure that we account for that. And this work is going to be F delta D cos theta. Okay, now if you were given MEA and you had a way to figure out MEB, you could actually figure out what the work is that way. But in this case, we don't know what MEB is, and we're being asked maybe what the velocity is at point B. So let's say we've been asked to get the velocity at point B. Well, in this case, we need to figure out what the work value is to allow us to isolate for that VB. So we can use the fact that work is equal to FD cos theta, and we can just figure it out from there. So I'm going to change the color here so we can actually see it. What force is causing that energy to be lost? Well, it's the force of friction. We know that that's mu Fn, which is the same as mu mg cos theta. Now you'll know that hopefully that this cos theta is 180 degrees here, so that gives us a negative work, and that should make sense because it will drop down the energy. In other words, the energy that you end up with is less than the energy that you began with, and the only way you can get that is with a negative work value. So we would have to figure out what mu mg is equal to there. So we'd have to multiply them together, mu times g times m. So mu times m is going to give us 0.5, and we multiply that by g, and we will get 5, and we're going to get a negative 5. And of course, work is going to be in joules. So we have to put that in here, and we've got to account for it. We can put our work value in here. It's going to be a negative 5 joules. We have all that we need here to figure out what we begin with in terms of mechanical energy. So G times H is going to be 100 times 10. Again, we're just using the fact that we're saying the acceleration due to gravity is 10, just to keep things simple. So we have 100 times 10, which gives us 1,000 joules. There wasn't really a lot of work done, which is mainly because of that mu k, which is a crazy small value. It's probably going to be more than that. But we have our VB squared over 2 is equal to 1000 minus 5. So we can, of course, solve from here. We would get 2 multiplied by 995 joules is equal to VB squared. And so VB is equal to the square root of that. And that would be in meters per second. So just to recap, we need to assume that it's a closed system unless told otherwise. If it's an open system, you'll have enough to hopefully be able to figure things out, and you have to account for that work that's happening to add energy to the system or remove it from the system. So just to recap on key points, if you're given a conservation of energy problem, you need to classify the system as either open or closed. And you need to figure that out nice and quickly. You need to label your different events, that could be labeled as 1, 2, or 3, or we saw in our practice problems A and B. These are events, different points in time. You need to set up your COE equations, so ME1 is equal to ME2. Sometimes you will also see this written as ME equals ME prime, or before and after. You need to set a reference height as h equals 0, you decide that. And you need to solve for your unknown value, whether that value is work or VB or whatever the case may be. Okay, so that's just how to solve a conservation of energy example for a closed system and an open system.